is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we discussed shear force and bend moment diagrams for overhanging beam subjected to point load and uniformly distributed load. Here, when a load is acting on a beam, that is particularly vertical loads, it bends or it deflates because of action of the loads. The amount of which the beam bends generally depends upon the amount of as well as the type of the loads, length of the beam, elasticity of the beam, and type of the cross section of the beam. The scientific way of studying the deflection or any other effect generally done by drawing the shear force and bend moment diagrams by analyzing them. The shear force means it is defined as the algebraic sum of the unbalanced vertical forces acting on a beam toward the left side or right side of the section considered. Bending moment. The bending moment at any cross section of the beam is defined as the algebraic sum of the moments created by the forces to the right or left of the cross section. Generally, the beams are classified as cantilever beam, simple supported beam, overhanging beam, rigidly fixed or built-in beams, and continuous beams. The cantilever beam means which is a fixed one end and the other end is free is called cantilever beam. The distance between the fixed end to the free end is treated as the length of the beam. The simple supported beam, it is a beam which is freely supported over the supports at its ends. This supports it may be the ball point or knife edged supports. Since it is freely suspended at its center, at its supports, the moments at this point is treated as 0 now. The overhanging beam, a beam is projected at one side or both sides of the supports. Then the type of beam is called overhanging beam. Here it is shown here now. Here this figure is representing now A. The beam is projected on both sides of its supports. But if you take another beam now B, here one end is here supported with the here edge and other is supported there now, but the other end is projected behind the support as shown in figure now. So that means the overhanging beam is the beam which is maybe projected on both sides of the supports or one side of the support. Fixed beam, a beam whose both ends are fixed now, is known as fixed beam. Sometimes it is also called built-in beam and is also called encasted beam, which is shown in figure A now. The continuous beams, a beam which is provided more than two supports, is known as continuous beam, which is represented here now in figure number D now. A cantilever simple supported beam, that is one end of the beam is fixed and the other end is having support, and this support it may be knife edge or roller support. It is freely suspended over it. This type of beam is called cantilever or simple supported beam. Generally, these beams may be subjected to the the following types of loads. One is a point load. Sometimes it's also called concentrated load, uniformly distributed load, and third one is a uniformly varying load. Here overhang beam and point of contraflexion. Here the overhang beam is it is treated as the combination of simple supported beam and cantilever beam as shown in figure. For the purpose of shear force and bending moment diagrams, the overhanging beam is analyzed as combination of simple supported beam and cantilever beam. Point of contraflexion. The overhanging beam is analyzed as a combination of simple supported beam and cantilever beam. The bending moment in a cantilever is negative, and in case of simple supported beam, the bending moment is the positive. Since we are now considering it is a combination of cantilever and simple supported beam, the point somewhere, the bending moment which is acting on the beam, it crosses or changes signs from positive to negative or negative to positive. The point at which it crosses the axis of the beam or the bending moment is changing its sign from positive to negative is known as contraflexion. Here, taking one example, an overhanging beam ABC is loaded as shown in figure. Draw the shear force and bending moment diagrams and also find the contraflexure if any. Okay, the given data in the problem is the length of the beam is given 3 meters plus 1 meter, that is totally 4 meters. It is subjected to uniformly distributed load entire its length at the rate of 4.5 kilonewtons per meter. The overhanging length of the beam is given 1 meter. The distance between the two supports, which is considering here as simple supported beam, having 3 meters. So for the solution of this problem, it is similar to the problems of simple supported beam. In this case, the first step is determine the reactions at A and B respectively. Since the beam is in equilibrium position, it has to satisfy the two conditions. One is the sum of the vertical forces acting on the beam should be equal to 0. The second one is the moments created by the forces at any point should be equal to 0. By using these two conditions, it is required to determine the values of RA and RB, that is the reaction forces at A and B now. So based on the first conditions, the sum of the vertical forces acting on the beam should be equal to 0, or in other words, the sum of the forces which are acting downward direction should be equal to the sum of the forces acting in upward directions. Here, RA and RB, the reactions at A and B, they are acting upward directions. The total load which is kept over the simple supported beam, that is 4.5 kilonewton per meter, that is the uniformly distributed load, is acting in downward directions. Hence, RA plus RB is equal to, you can take it to 4.5 into, that is the rate of loading, 4.5 kilonewton per meter. Total length is given 4 meters, hence which is equal to 4.5 into 4 is equal to 18 kilonewtons. Now, second equation is taking the moments at any point. Here the preferable point is always toward the left side of the beam. Here I am taking here now at A point, that is sigma MA. We can take it as the the moments at a point A is equal to, in this case, RB, the beam is here the reactions, tends to rotate the body in anti-clockwise directions. So generally it is treated as here positive. So RB into the distance is equal to 3. But the total load is there now, that is 18 kilonewtons, which is acting downward directions. It tends to rotate the body in clockwise directions. So clockwise direction is here treated as negative. So total load is equal to 4.5 into 4. It is there, but it is acting, this entire force is acting at the center of gravity, or in other words, at the middle. That is nothing but we can take 4/2 now. But it should be equal to 0. Just we are taking it equal to 0 now. Okay, from this relationship we got now RB into 3 is equal to 4.5 into 4 into 2 now, 2, which is equal to 36 now. RB is equal to 36 by 3, it is equal to 12 kilonewtons. Since RA plus RB is equal to 18 kilonewtons, hence RA is equal to, you can take it as here 18 minus 12, it is equal to 6 kilonewtons. Now, after determining RA and RB, determine the forces, shear force acting at various position to draw the shear force diagram now. In order to draw the shear force diagram, first of all, draw the beam as per the suitable scale and represent the load acting on it at various points. Then draw the vertical lines in downward directions of through various counters. Here now. And draw an horizontal lines. It is a convenient distance to represent the length of the beam. Since the shear force is a positive for the cantilever beam, and for the simple supported beam, toward the right side is negative, toward the left side is positive. Hence, keep sufficient space above as well as below the reference line now. After drawing now, the shear force at the free end of the cantilever beam is always equal to 0 because of uniformly distributed load. Here it is 0. When it is moving toward the left side of the beam now, that is from B to C to here now, B position now. The load acting on the beam is gradually increases. Finally, it reaches here now. Here total load is equal to at this point 4.5 kilonewtons now. That is, it is increases up to this position now. The shear force now at B is equal to, it is becoming now, that is 4.5, it is moving, acting in downward directions, but upwards, that is reaction force is given 12 kilonewtons. So the resultant force is equal to that, thus algebraic sum of these two forces, that is equal to RB is equal to, we can take it as here plus 4.5 minus 12, which is equal to 7.5 kilonewtons. So the resultant force is equal to 7.5 kilonewtons acting at the support B. Hence, draw line to represent the 7.5 kilonewtons downward directions. So while representing the forces, select a suitable scale. Here according to this figure now, 1 kilonewton is equal to, you are taking 5 mm now. Otherwise, just to take 10 mm, but it becomes more in length now. That is more space is required. Hence, I am taking 1 kilonewton, nothing but represent the 5 mm now. So here now 7.5 kilonewtons. Just select the scale. So according to 1 kilonewton is equal to 5 mm now in downward directions now. And again, the shear force at A is equal to, since there is no force is acting additionally, or the beam is not overhanging other side, so it is equal to the reaction force which is acting at end A. According to the problems, we got to the reactions at A is equal to 6 kilonewtons. Hence, draw the 6 kilonewtons. Here it is a positive 6 kilonewtons, here is 7.5 is the negative. But it is changing from positive to negative according to the straight line law because it is subjected to only uniformly distributed load. Hence, join these 2 points, that is here now, by using straight lines. This diagram is known as shear force diagram for the cantilever overhanging beam. Now, the shear force is crossing the axis of the beam at a point M is represented. That means at this point the beam is possessing maximum bending moment. So the maximum bending moment where it is up, the bending moment at which it is having can be located by using the two similar triangles now. Here A dash, M, here I am taking B and B dash point now by using. So here if I take this is equal to the distance between A and M is equal to X. The remaining distance is treated as 3 minus here X now. So by using these equations now, we have to determine, we have to locate the position of the point M at which the beam is possessing maximum bending moment. So here now X by 6 is equal to, because we are taking similar triangle, it is equal to 3 minus X divided by 7.5 now. So from this relationship we got X is equal to 1.33. That means at a distance of 1.33 the beam is possessing maximum bending moment. Now bending moment diagrams. According to the fundamentals of simple supported beam, the bending moment at the supports it should be 0 because it is freely suspended. But in the case of overhanging beam, the bending moment is not equal to 0 at B position because it is subjected to certain loads now. Here the bending moment at A is equal to, it is given 0, that is we can take it as MA is equal to 0 now. Similarly, the point C is representing it is the end of the cantilever beam where the bending moment is equal to 0. Hence, we can take the bending moment at C is equal to, generally we calling MC is also equal to 0 now. Now that means MC is equal to 0. We required one more point at B now. The bending moment at a point B is equal to, we have to consider the load which is acting toward the right center of the beam, which is equal to, that is 4.5, it is a Newton per meter it is acting. The distance is given 1, but it is acting at the middle of the beam only because at its center, point of application of the torque, that is uniformly distributed load is at its center of gravity. Hence it is equal to, we can take 1 by 2 now. Okay, from this relationship we got to 4.5, 1 and 1 by 2 is equal to 2.25 now. But this bending moment is always rotate the beam in clockwise directions now. Here, the effect of the beam is having hugging effect. That means its center is, that is a convexity at the top. Hence, the bending moment is treated as negative values. So, it can take which is equal to minus of 2.25 kilonewton meter. That is at MB is equal to 2.25 kilonewton meter. Now, that means from here now, from 0 here now. Downward direction is 2.25. Since it is subjected to uniformly distributed load, join these 2 points by using parabolic curve. Now, the bending moment at a point M now. The M is the point at which the bending moment is the maximum. Hence, M is equal to, we are taking here now, considering the forces which are acting toward the left hand side of the beam. Here toward the left side, that reaction is there, RA. Distance is equal to 1.33. The effect is sagging effect it is having, hence it's a positive. Here now. And the load is there now. That is uniformly distributed load between A and M. It is a hugging effect. So it is negative. That is total force is equal to 4.5. The length is equal to 1.33. But it is acting 1.33 divided by 2 now at the middle now. So by using this calculations we got which is equal to 4 kilo Newton meter now. So at this point it is having 4.4 kilonewton meter now. Okay, join these points, these 2 points by using the smooth curve. It is known as a parabolic path now. And here now, join that M with the A by smooth curve, that is a parabolic curve. This is known as the bending moment. Here one point is there now, that at which the sign of bending moment is changing from positive to negative. The point at which it is changing its sign positive to negative or negative to positive is called contraflexure. So we have to look at the position of contraflexure. That means at which the bending moment possessed by the beam is equal to 0 now. So let P be the point of contraflexure at a distance of y from the support here now. We are taking, assume at this point, it is there now, assume. Now the bending moment at here P is equal to, we can take it as MP. At this point, assume just nothing but somewhere at this position now, we are taking y now. It is equal to here RA into y, it is a positive. The load is there now 4.5 kilonewtons into at a distance of y, but it is acting at a middle now y by 2, but it should be equal to 0 required now. Since y is not equal to 0, we can take it as RA minus 4.25 into y by 2, it should be equal to 0 now. RA is equal to, already we determined it is equal to 6 now. That is 6 minus 4.5 into y by 2, it should be equal to 0 now. Okay, from this relationship we got y is equal to 2.67 meters from the end to end. Okay, this is the way of identification of shear force across the section of the beam as well as the bending moment also, and determine the point at which the bending moment is changing its sign from positive to negative or negative to positive. It is also called contraflexion. So one more problem. A beam ABCD as shown in figure 4 meters long is overhanging by 1 meters and carries a load as shown in figure. Draw the shear force and bending moment diagrams for the beam and locate the point of contraflexion. Here, if we observe the figure now, the beam is projected toward the left side of its support, that is the point A according to the problem here given. It is a B now. That is the points is given A, B, here now C and D is given now. That means the projected means between A and B, or it is nothing but with respect to the supported B, it is projected toward the left hand side now. Now, first of all, draw the beam as per the given dimensions by selecting suitable scale and represent the forces which are acting on it now. The given data in the problem is the length of the beam L is equal to 4 meters, that is 1 meter, 1 meter and 2 meters now. Uniformly distributed load over a beam AB is given now, here now, that is the projected area, which is equal to 2 kilonewton meter. That means the total load acting on it is equal to only 2 kilonewtons because the length is also given 1 meter. The point load at C is equal to, is given now, 4 kilonewtons. Now, in order to draw the shear force diagram as well as the bending, first of all, draw the lines, vertical lines, downward directions passing through the various points, the key points like this. And at a suitable position now, draw the horizontal lines. But while taking here the line, it should be the bend shear force is the positive as well as the negative for the simple supported beam. And since it is acting toward the left side, the shear force is here negative now. So the values are given now. Here first in the first step the problem is determine the reactions at A and B. Otherwise difficult to determine the values of shear force as well as the bending moment acting at various position now. So since the beam is in equilibrium now, that means sum of the forces acting upward direction should be equal to the sum of the forces acting in downward directions. Or in other words, RA plus RB, both are the reactions forces acting upward directions. It should be equal to here 2 into 1, that is the uniformly distributed load, and 4 kilonewtons the point load is acting, that is equal to 6 kilonewtons is acting downward directions. Or in other words, RA plus RB is equal to 6 kilonewtons. Taking the moments at a point B and equating to 0 because the moments created by the forces at any point on the beam should be equal to 0. From this relations here now, here from this point, here RD into 3 now, that is the reaction force into here RD. It tends to rotate the body in counterclockwise directions, and 4 kilonewtons force is there in clockwise directions, and 2 kilonewton per meter the load is again acting anti-clockwise directions now. That is the sum of the forces which are acting perpendicular to the axis of the beam should be equal to 0. The second equation is the moments created by the forces at any point should be equal to 0. That's why we have taken the moments at a point D now. Here R into T3, it is equal to 4 into 1 because we are taking here RD, the moments at a point, so we are taking MB, it should be equal to RD into the distance between B and D is equal to 3 now. It tends to rotate in anti-clockwise direction positive. After that 4 kilonewtons is there now. That is acting, tends to rotate the body in clockwise directions. That is 4 into 1 meter negative. But the uniformly distributed load which is acting toward the left side of point B, again it tends to rotate the body in here clockwise directions now. So this load is acting in anti-clockwise directions, and so again to the positive, which is equal to 2 kilonewtons, here 1 into 1 by 2 now. But it should be equal to 0 required now. So from this relations we got to R into 3 is equal to, when we are taking 4 into 1 positive minus of 2 into 1 into 1 by 2, which is equal to 3 now. RD is equal to 3 by 3 is equal to 1 kilonewtons. That is the reaction set to D is equal to 1 kilonewtons. But we are having RA plus RB is equal to 6, and so the reactions at B is equal to, here this value is equal to 5 kilonewtons now. Now after determining the reactions, draw the shear force and shear force diagram. So already we drawn the lines now, in distance. Here with respect to the point D now, the shear force which is acting toward the right side in upward directions are treated as a negative. Hence, here draw the vertical lines in downward directions by selecting suitable scale. Here suitable scales means I am taking here now 10 mm is representing 1 kilonewtons now. So here now 10 kilonewtons. Since there is no force is acting between here D as well as the C now, hence it is treated as just horizontal lines up to this position. Again, the shear force at C is equal to, is given now. Here 4 is the, here 1 is the negative, 4 is the positive, hence 3 kilonewtons force that is acting, that is the positive. Hence, draw the vertical lines upward directions from this place to, from C to this position to represent the 4 kilonewtons additionally. So it goes the resultant to, that is 3 kilonewtons. 3 kilonewtons is nothing but equal to 30 mm upward directions. Afterwards, there is no force is acting between C and B now, and draw the horizontal line. Now coming from the A point now, here the shear force at A is equal to 0, and moving toward the point B, it is a simple support, it is the uniformly distributed load, hence it follows the straight line law. The load is acting 2 into 1 now, that is 2 kilonewtons, draw the 2 kilonewton and downward directions. Now join these points with this one now. This is the representing the reactions at a point to A now. This diagram is known as shear force diagram for the beam. Bending moment diagrams. Okay, the bending moment at D is equal to 0. Bending moment at A is also equal to 0 because these are treated as free end of the beam now. Now bending moment at a point to B required now. At this point. Here B, it is equal to, the bending moment at B is equal to MB, which is equal to 2 into 1 into 1 by 2 now. So which is nothing but equal to 1 kilonewton meter now. But it tends to rotate the body in such a way that it is having hugging effect now. Hence it is treated as a negative now. So from this point draw lines in downward directions 1 kilonewton meter as per the scales to represent the bending moment at a point B now. Now the bending moment at a point D is equal to 0. I am taking bending moment at a point C required now, because you can take from the left side or right side according to your convenience now at C now. Now considering the forces toward the right hand side, only one force is acting now, that is MC is equal to, I can take it as that is 1 kilonewtons that is acting into 2 now, or in other words it is equal to 2 kilonewton meter. So from C draw vertical lines now, draw lines to represent the, using the straight lines to represent the variation of the bending moment from D to C position now. Again, there is no force is acting between C and B now, hence join the points by using the straight line law now. This diagram is known as bending moment diagram. Just on observing this figure now, at one point, that is at P now, the bending moment is crossing that is the axis of the beam now. The point at which the bending moment crossing the axis of the beam is called contraflexure. So we have to look at the position of contraflexure of the beam also now. Here, you not get this point now. Just I am considering here the one triangle, the one more now. This length already determined, it is equal to 1 now. It is equal to 2. The distance between these 2 points is equal to here now 1 meter. Assume this is equal to y now. So I am giving the points now here now. Here B point, B dash, here C, here 2 and P now. That is here now 1 B B, here one figure, and C 2 B, both are similar triangles now. That means similar triangle means the ratio of corresponding sides length should be equal. Hence, here 1 by y is equal to we can take it 2 into 1 minus y now. Okay, from this relationship we got y is equal to 1 by 3, or it is also equal to 0.33 meters. This is the position of the contraflexure from the support B as shown in figure. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.